go up to down. So if we look at these 9 graphs, okay, these are 9 graphs with a bunch of different things going on. The question is which graphs have the same end behavior and which graphs have have opposite end behavior, meaning they go down, up, or up, down. So as I'm gonna go through this and just identify them real quick. You can mute this if you want and figure this out as you go. This is up, up, because that parabola ends up going up. This crazy graph is, notice it's degree 6, but that is also up, up. I should stay consistent and just call it UU. So, and then C is up and down, because the left side goes up and the right side goes down. As we work through this, again, just kind of buzzing through, this is up, up, this is down, down. Y equals x to the third is a down, up graph. This crazy looking one, negative x to the fifth, is up and down, 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 and this is down and up. So, there's all 9 of them. Which graphs have the same end behavior, meaning go the same way? That would be graphs A, B, which one are the ones? D, E, H. D, E, and H are the graphs that have the same end behavior, and then the opposite end behavior would be C, graphs C, F, G, and I. So those are my C, F, G, and I. Now, that might not seem all that interesting, or yeah, who cares? But something that is interesting comes up if you look at these things. All of these 5 graphs that were yellow, if you look at their equations, they all have something in common. And that is that the degree of them are all positive. So if I look, all of these graphs are x to the second, or x to the fourth, or x to the sixth, and that is not a coincidence. That degree of the graph actually will help us to determine the end behavior. And then all the ones that are highlighted blue with the opposite end behavior, those are degree 3, degree 3, degree 5, and degree 5. So, if the degree is even, it's either going to be up, up, or down, down. And then if the degree is odd, it's going to be up, down, or down, up, which is kind of interesting. And then the other thing that can help us decide between them, if you look at D and E, graph D is an up-up graph, and graph E is a down-down graph. Just like with parabolas, that front number tells us everything, or what we call the A value. Here, if A is negative, it's going to be down-down. Here, A is a positive x to the fourth, so that's going to be up-up. So actually, when written in standard form, the first term will tell us a lot about the shape of the graph. Not so much what goes on in the middle, but for sure what happens on the outsides. So if we put all this together real quick, we're going to make this graphic organizer in class, but go ahead and just make this a little T-chart in your notes. If the end behavior, we're going to start with the degree. So if the degree is odd, and it is and the A value is greater than 0, meaning the A value is positive. An odd degree, one way I like to think of it as odd, starts with the word O, odd starts with the letter O, meaning that the end behaviors are going to be opposite. So it's either going to be down, up, or up, down. Since the A value is positive, that tells us a positive A value means it will always end with up, and The odd degree means that the end behaviors must be opposite, so it's down and up. If we keep this sort of pattern going, you'll see that if the degree is odd, but we switch the a value to be less than 0 or negative, then the end behavior switches to up and down. If the degree switches now to even, the a value is positive or greater than 0. An even degree means that the end behaviors must be the same, so it'll either be up, up, or down, down. But as we know with parabolas, a positive a value means that it opens up. And so if you have an even degree but a is less than 0, that is going to be a down, down graph. So all of that information comes from just the first term. So that first term tells us whether or not it is going to, what's going to happen at the ends of the graph as you go to the right and to the left. So we've talked about binomials, trinomials, like classifying. We've talked about degree, and both of those will help set up what the end behavior is. So the last thing we have to talk about today is what is a turning point. And a turning point is simply where the graph switches from increasing to decreasing, or vice versa. So where does the graph go? Where does the graph switch from going up to going down? Or where does it switch from going down to going up? So if you look at this polynomial graph, it's decreasing, decreasing, and then it switches to increasing. So this right here, that point is one turning point, and then from there the graph increases, increases, hits a maximum, and then it comes back down. So this is another turning point. In calculus you call them local maximums and local minimums, but we're not going to get into that here. So this has two turning points. Two turning points. Now, what that tells us is since it has two turning points, the smallest degree that this graph could be is always one more than the number of turning points. So two turning points means this thing is a minimum of degree 3. Because it has opposite end behaviors, meaning the end behavior is up and down, it has to be an odd degree. So this thing is either going to be degree 3, or if it's not degree 3, it could be degree 5, degree 7, degree 9, but it has to be odd. So the turning points will tell us, if you add 1 to the turning points, that tells you what the smallest degree is from a graph. So we're putting all these pieces together just to kind of get as much information as we can. So if we look at a graph like this, we see that the end behavior is down and down, down and down, which means it has the same end behavior, so it must be an even degree. So x to the second, x to the fourth. Obviously this graph isn't x to the second power because this isn't a parabola. When we say sine of LC, this means the leading coefficient. I think I'm going to switch this to be what is the sine of A, meaning is the front number positive or negative. And that we don't know because we don't have the equation, but we know since the end behavior is down, down, that A must be less than 0. If you go back to that graphic organizer, the down, down box right down here tells us that the degree must be even and A must be less than 0. So we know for sure that it's going to be like negative x to the fourth or negative x to the sixth, something like that. If we count the number of turning points, I have 1 there, 2 there, 3 there. So since there are 3 turning points, we already know this, but the least degree is 4. It could be 6, 8, 10, so on. But the key is it cannot be degree 2 because it has 3 turning points. And for now, that's all we're going to do with the graph. We'll get into a little bit more of this later in the chapter, and I believe it's actually next trimester that we do that. So, here's one that's a little bit goofy. Again, if you look at the end behavior, this goes down to up, which means since it has opposite end behavior, I know I'm dealing with an odd, but since the graph ends by going up, we know that a must be greater than 0. It has a positive a value because it's increasing. The turning points, now this is a little tricky to see. This graph is increasing, and even though it gets close to flat, it never actually switches to decreasing. So this has 0 turning points in it, which by our definition means that the least degree of this graph would be degree 1. We know it's not degree 1 because a degree 1 graph has to be a straight line, has to be a linear. So just by the shape of the graph, we know it's actually probably degree 3, or it could be 5, or 7, or so on. So again, right now I know this is a lot of vocabulary and a lot of new things, but between the end behavior and the a value, we can figure out ballpark what we're working with as far as a graph is concerned. The final thing we're going to do in this lesson, and I'll wrap this up, is we can figure out what degree a graph will be based solely on the table. And this goes back to the warm-up. So if we look at this table of values, I see that the x coordinates are all going by 1s, and I don't really care so much to look at that. I want to pay more attention to what's happening here. So what we're going to do when we find how far is it, or what's the difference from -8 to -5, that is an increase of 3. -5 to 1 is an increase of 6, and 1 to 10 is an increase of 9. I know this isn't going to make a straight line because these would all have to be the same. If this graph was linear, it would have to be +3, +3, +3. But it's not. But what's nice about this is that if I do what are called the second differences, so what's in blue, this in blue, these are called the first differences. In green then, when I find the difference of the differences, this is called the second differences. So from 3 to 6 is an increase of 3. Switch greens on you there. From 6 to 9 is an increase of 3. And if we kept this pattern going, we would see that the second differences, so the second differences are the same. They are consistent. They are equal, however you want to think about it. And because the second differences are the same, that means this table, if you were to graph it, would make a degree 2 polynomial. So the degree of the polynomial will always match when are the differences the exact same. So if the second round of differences are equal, then it's degree 2. If we had to go one more time to the third differences, then it would be degree 3. So that's just another way to find the degree without actually graphing it. And there's no second guessing here. This is just very clear. So if we were to go back, sorry to do this, but if we scroll back all the way to the warm-up problem, oh boy, I'm sure there's an easier way to do this. Since we had to go, these were our first differences, second differences, third differences. This graph, if you graphed those y values, this would be degree 3, or x to the third, some sort of x to the third graph. So our final one is a u-try. If you want to pause it and try it yourself, go ahead, but I'm just going to buzz through and get this done. So from 70 to 59 is down 11, 59 to 56 is down 3, 56 to 57 is up 1, and the same thing from 57 to 58 is up 1. These are not all the same, so this cannot be degree 1. So we go to degree 2. Negative 11 to negative 3 is adding 8. Negative 3 to positive 1 is adding 4. And 1 to 1 is adding none. Again, not the same. The second differences are not equal, but you can see a pattern here. From 8 to 4, I'm